Today, I want to take you on an incredible journey through one of the most mind-boggling questions humanity has ever asked. How big is the universe? But before we dive into the endless depths of space and time, if you find yourself amazed by the mysteries of the cosmos, don't forget to like and share this video so others can join this journey too. The universe. Just that word alone sparks wonder and curiosity. It's everything we know, and yet, it is far beyond what we can truly comprehend. It stretches in all directions, beyond the grasp of our imagination, filled with stars, galaxies, dark matter, and mysteries that challenge even the brightest minds. To ask how big the universe is might seem simple, but the answer takes us to scales so vast that numbers themselves start to lose meaning. First, let's start with what we see. When we look up at the night sky, the stars twinkling above seem close, but in reality, even the nearest star is millions of times farther than the moon. The moon, glowing softly in the night, is about 384,400 kilometers away, already a huge distance for us here on Earth. But the closest star beyond our sun, Proxima Centauri, is about 4.24 light-years away. What does that mean? A light-year is the distance light travels in 1 year, roughly 946 trillion kilometers. So Proxima Centauri is more than 40 trillion kilometers away. These numbers are so large they're hard to picture. Yet, Proxima Centauri is just our nearest stellar neighbor. Our sun is part of a sprawling galaxy known as the Milky Way. This galaxy contains hundreds of billions of stars, all bound together by gravity in a magnificent swirling disk about 100,000 light-years across. To travel across our own galaxy at the speed of light would take 100,000 years, a span of time so immense it dwarfs human history. Our ancestors, walking the Earth tens of thousands of years ago, would only just be able to imagine a journey across the stars if they could travel at light speed. But the Milky Way is only one galaxy among billions. When astronomers gaze into the depths of the universe with powerful telescopes, they find galaxy clusters, groups, and enormous superclusters. These cosmic structures stretch over millions, even billions of light-years. The universe is expanding and every galaxy is moving away from us, carrying with it the imprint of the universe's birth, the Big Bang. To understand the size of the universe, we need to grasp a few concepts about the fabric of space itself. The universe has been expanding since its birth approximately 13.8 billion years ago. This expansion means that distant galaxies are not just moving through space, they are being carried away as space itself stretches. Because of this, the observable universe, the part we can see, is about 93 billion light-years in diameter, much larger than you might expect given the universe's age. The observable universe is a cosmic horizon set by the speed of light and the age of the cosmos. Light from beyond this horizon simply hasn't had time to reach us yet. But the universe beyond this horizon could be infinitely larger, perhaps even infinite. We simply cannot see or measure it. To illustrate how big this is, imagine the Earth is the size of a grain of sand. The observable universe, by comparison, would be the size of the entire Earth's surface and beyond. Every star we see is a sun with its own system of planets, orbiting in vast cosmic neighborhoods. The number of stars in the observable universe is estimated to be around 1022 to 1024. That's a number with 22 to 24 zeros. To put that in perspective, it's more stars than all the grains of sand on every beach on Earth combined, multiplied, many times over. And stars are only part of the picture. The universe is filled with invisible dark matter, which outweighs normal matter by about 5 to 1. Even stranger is dark energy, a mysterious force driving the accelerating expansion of the universe, making up roughly 68% of its total energy content. These unseen components shape the large-scale structure of everything around us, yet remain some of the greatest puzzles in physics. In terms of sheer scale, the distances in the universe push our minds beyond everyday experience. Light travels at nearly 300,000 kilometers per second. Even at this incredible speed, it takes about 8 minutes and 20 seconds for sunlight to reach Earth. The nearest galaxy, Andromeda, is about 2.5 million light-years away. That means the light you see from Andromeda left there long before humans even walked upright on Earth. As technology advances, we continue to push the boundaries of what we can observe. The Hubble Space Telescope has shown us galaxies billions of light-years away, looking back in time toward the universe's infancy. Future observatories will peer even deeper, revealing the cosmos in unprecedented detail. But no matter how far we look, the universe continues to surprise us. Black holes more massive than millions of suns, mysterious bursts of gamma rays, and cosmic filaments stretching across unimaginable distances remind us that the universe is a place of both beauty and enigma. Numbers alone cannot capture the full wonder of the cosmos. They stretch beyond what the human mind can easily grasp. Yet by trying to understand these numbers, by contemplating the vastness of space, we touch something profoundly human. The desire to know our place in the grand scheme of existence. So, how big is the universe? It is a question that opens doors to endless exploration and awe. From the tiny particles that make up everything to the sprawling galaxies that light up the cosmic night, the universe is a vast, beautiful mystery, inviting us to keep searching, keep wondering, and keep dreaming. When we speak about the universe's size, we must understand that the universe is not just vast, it is staggeringly large beyond human intuition. The mind struggles to hold such enormous scales in perspective because our everyday experiences involve distances measured in meters or kilometers, a tiny fraction compared to cosmic scales measured in light-years and parsecs. A parsec, by the way, is another astronomical distance unit equal to about 3.26 light-years, or roughly 30.9 trillion kilometers. Using these units helps astronomers navigate the immense distances between stars and galaxies. To further explore how huge the universe is, let's zoom in and then zoom out, looking closer at familiar neighbors and then expanding our view to the cosmic horizon. Imagine the Earth again, now as a marble, a small globe cradled in your hand. Around this marble swirl the planets of our solar system, but even these, in comparison, are minuscule specks on a cosmic scale. The Sun itself is so large that about 1.3 million Earths could fit inside it, but the Sun is only one of more than 100 billion stars in the Milky Way. The Milky Way galaxy is a massive island of stars, gas, and dark matter shaped like a spiral, rotating slowly over hundreds of millions of years. We are located about 27,000 light-years from its center, in one of its spiral arms. The Milky Way's gravitational pull holds all its stars and material together, but it is just one of many galaxies in the universe. Nearby, we have the Andromeda Galaxy, our closest spiral galaxy neighbor, located about 2.5 million light-years away. Even at this distance, Andromeda contains approximately 1 trillion stars, about twice the number of stars in the Milky Way. Andromeda is on a slow collision course with our galaxy, but don't worry. That event will happen billions of years from now, long after our Sun has transformed into a red giant and faded away. Beyond the local group of galaxies, we find galaxy clusters, collections of hundreds or thousands of galaxies held together by gravity. One such cluster is the Virgo cluster, about 53 million light-years away, which contains thousands of galaxies. And even clusters themselves group together into superclusters, vast regions of space that span hundreds of millions of light-years. Yet, these structures are just the visible part of the cosmic web. The universe's large-scale structure looks like a vast network of filaments, thread-like chains of galaxies and dark matter, with enormous voids between them where few galaxies exist. This cosmic web is shaped by gravity pulling matter into denser regions over billions of years. Scientists estimate the number of galaxies in the observable universe to be around 2 trillion. This is a revision from previous estimates that counted only hundreds of billions. New deep space observations revealed many faint small galaxies we hadn't seen before. Multiply these countless galaxies by hundreds of billions of stars each, and the total number of stars in the observable universe reaches numbers so huge, it is almost impossible to grasp. Think about the light from these distant stars and galaxies traveling for billions of years, crossing the dark void to finally reach our telescopes. When we look out into space, we are essentially looking back in time, seeing ancient light that tells us about the universe's past. Some of the farthest observed galaxies are seen as they were just a few 100 million years after the Big Bang, revealing how the universe began to form stars and galaxies. Yet, despite the universe's mind-blowing size, it is only the observable part we can see. The entire universe might be infinitely large, extending beyond what light has reached us so far. If it is infinite, then space goes on forever, with galaxies continuing in every direction. This is a concept that challenges our everyday understanding of space as a finite place. Moreover, the shape and geometry of the universe play a crucial role in how we perceive its size. Cosmologists use data from the cosmic microwave background, the faint afterglow of the Big Bang, to study the universe's curvature. Measurements show that the universe is remarkably flat on large scales, meaning that parallel lines remain parallel, and the geometry follows the rules of Euclidean space. This flatness suggests the universe is either infinite or so large that we cannot detect its edges. Beyond these vast distances, the universe also holds mysteries about its age and expansion. The universe's expansion rate, measured by the Hubble constant, tells us how fast galaxies are receding from each other. This expansion causes the observable universe's edge, the cosmic horizon, to grow continuously, revealing more of space as time goes on. However, this expansion also means that some galaxies are moving away from us faster than the speed of light due to space itself stretching. These galaxies will eventually disappear beyond our cosmic horizon, making them forever unreachable. This limits the portion of the universe we can ever explore or observe. While we think of the universe as unimaginably huge, it is also surprisingly uniform on large scales. When we look at the cosmic microwave background radiation, we see an almost perfect temperature uniformity across the sky. This uniformity hints that the universe began in a hot, dense state and expanded rapidly during a period called inflation, smoothing out any irregularities. The numbers involved in describing the universe's size extend beyond human intuition, but provide a glimpse into the profound scale and beauty of the cosmos. The universe is a realm where vast distances separate stars and galaxies, where time and space weave together into a tapestry far larger than our home planet, and where the tiniest particles and the largest cosmic structures coexist in a delicate balance. Our efforts to measure and understand these scales come from centuries of astronomical observations, theoretical physics, and advances in technology. Every telescope, every satellite, every data point adds a piece to the puzzle, revealing how big and complex the universe truly is. We stand as observers on a small planet orbiting an ordinary star in one galaxy among billions. Yet, from this tiny vantage point, we gaze outward and inward, exploring the cosmic vastness and the microscopic world of particles that build everything we know. The universe's size is not just a measure of distance, it is a story of creation, evolution, and the boundless mysteries that fuel human curiosity. As we contemplate the enormity of the cosmos, it invites us to reflect on our place in this grand expanse. We are made of the same elements forged in stars, connected to the universe. Through time and space, the universe's vastness does not diminish us. Instead, it highlights the incredible journey we have taken to understand and appreciate the world beyond our blue planet. To truly grasp the enormity of the universe, we must venture beyond distances and numbers, and into the story of how the universe itself came to be and grew into the vast cosmos we observe today. The universe's size is deeply connected to its history, a journey that began nearly 14 billion years ago with a cosmic event known as the Big Bang. The Big Bang was not an explosion in space, but rather an expansion of space itself. Imagine the universe as a balloon being blown up. Every point on the surface moves away from every other point as the balloon expands. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense, a singularity where The laws of physics as we know them break down. From this singularity, space began to stretch, matter began to form, and the clock of cosmic time started ticking. As the universe expanded, it cooled, allowing the first particles to form atoms, mostly hydrogen and helium. Over hundreds of millions of years, these primordial atoms clumped together under gravity's pull, forming the first stars and galaxies. The light from these earliest stars is still traveling through space, reaching us from billions of light years away, providing a window into the infancy of the cosmos. The expansion of the universe is not a mere relic of the past. It is ongoing and accelerating. Scientists discovered in the late 20th century that distant galaxies are speeding away from us faster than expected. This acceleration is attributed to a mysterious force called dark energy, which permeates all of space and pushes the universe to expand faster and faster. Dark energy makes up nearly 70% of the total energy in the universe, yet its nature remains one of the biggest mysteries in modern science. Because of this accelerated expansion, the universe's future is uncertain. Some theories suggest it will continue to expand forever, growing colder and emptier as galaxies drift beyond our view. Others propose a big rip, where the expansion eventually tears apart galaxies, stars, and even atoms themselves. Understanding dark energy is key to unlocking these cosmic secrets. The scale of time in the universe is just as staggering as the scale of distance. The Earth is about 4.5 billion years old, a tiny fraction of the universe's age. Our Sun formed roughly 4.6 billion years ago, giving birth to the solar system, including our planet. Life on Earth has existed for about 3.5 billion years, but only in the last few 100,000 years did humans appear. When we think of the cosmic timeline, our entire history is a blink of an eye compared to the universe's age. But the universe's size is not just about space and time. It is also about the structure and contents that fill it. Besides the stars and galaxies, the universe contains cosmic radiation left over from the Big Bang, known as the cosmic microwave background radiation. This radiation is a faint glow, detectable in every direction, providing a snapshot of the universe when it was just 380,000 years old, before stars and galaxies even existed. This cosmic microwave background is remarkably uniform, but has tiny fluctuations, minute differences in temperature and density. These fluctuations are the seeds from which all the large-scale structures like galaxies and galaxy clusters grew. The patterns we observe in the cosmic microwave background allow scientists to measure the universe's shape, age, composition, and rate of expansion with incredible precision. One of the most profound realizations in cosmology is that most of the universe's matter is not ordinary matter at all. About 85% of the matter in the universe is dark matter, an invisible form of matter that does not emit, absorb, or reflect light, but whose presence is inferred from its gravitational effects on visible matter and the cosmic structure. Without dark matter, galaxies would not hold together, and the universe would look very different. Scientists are still searching for the true nature of dark matter. It might be composed of exotic particles we have yet to discover, or it could be a sign that our understanding of gravity needs revision. Whatever it is, dark matter plays a vital role in shaping the universe on the largest scales. The universe's complexity and scale inspire awe, but they also remind us of the limits of human knowledge. We live in a tiny corner of space and time, yet with curiosity and ingenuity, we have developed ways to peer billions of light years away and billions of years into the past. This quest to measure and understand the universe's size is not just an academic exercise. It shapes our worldview and connects us to the cosmos. Every atom in our bodies was forged in the heart of a star. Every breath we take is connected to the air and water formed on this planet over billions of years. And every thought we have is a product of the intricate evolution of life within this vast universe. In contemplating the universe's size, we confront the profound truth that the cosmos is immense, ancient, and full of wonder. It challenges us to keep exploring, to keep asking questions, and to embrace the mystery that comes with the infinite. One of the most mind-expanding ideas about the universe's size comes from the concept of the multiverse. While our observable universe is enormous, some theories in modern physics suggest that it may be just one of many universes, each with its own distinct laws of physics, dimensions, and realities. This concept pushes the boundaries of what we consider the universe and challenges our understanding of existence itself. The idea of a multiverse arises from attempts to unify quantum mechanics and general relativity, the two pillars of modern physics that describe the very small and the very large, respectively. These theories hint at the possibility of multiple universes emerging from quantum fluctuations, or as separate bubbles in an eternally inflating cosmic landscape. If true, the multiverse could be infinitely large, containing universes vastly different from our own, with different physical constants, particles, and dimensions. Though we cannot directly observe other universes, the multiverse theory offers profound implications for why our universe is the way it is. It might explain why the fundamental constants of nature seem finely tuned for life, a puzzle known as the anthropic principle. If countless universes exist with different properties, only some would allow life to arise, and we find ourselves in one such universe simply because we can exist here. Even if the multiverse remains speculative, it invites us to expand our imagination and humility when considering the universe's size. Our universe may be just a tiny island in a vast ocean of realities beyond our comprehension. Returning to our own universe, the distances involved can be so extreme that astronomers use special methods to measure them. Parallax, the apparent shift in position of a nearby star against distant background stars, helps determine distances up to thousands of light years. Beyond that, standard candles like Cepheid variable stars and type Ia supernovae serve as cosmic mile markers, their known intrinsic brightness allowing scientists to calculate their distance based on how bright they appear to us. These techniques help build the cosmic distance ladder, a series of methods astronomers use to measure distances ever farther into space. This ladder is crucial for understanding how big the universe is and how it has evolved. The universe's vast size also means that light from distant objects is stretched to longer wavelengths, a phenomenon known as redshift. This stretching occurs because as the universe expands, the space between objects grows, elongating the light waves traveling through it. By measuring redshift, astronomers can estimate how far away an object is and how fast it is moving away from us. Redshift is like a cosmic Doppler effect, telling the story of the universe's expansion. The higher the redshift, the farther away the galaxy, and the earlier in cosmic history we are seeing it. Some of the most distant galaxies have redshifts greater than 10, meaning their light has traveled over 13 billion years to reach us. Understanding these measurements reveals not only the universe's size, but also its history and fate. The cosmic scale is intertwined with time itself. The farther we look, the further back in time we see. This temporal dimension adds richness to our picture of the cosmos. Another fascinating aspect of the universe's vastness is the sheer number of planets orbiting stars. Recent discoveries from telescopes like Kepler and TESS show that planets are common throughout our galaxy, and likely throughout the universe. Estimates suggest there could be billions of Earth-sized planets in the Milky Way alone. If the universe contains billions of galaxies, each with billions of stars, and many of those stars host planets, then the number of planets in the observable universe could be mind-blowingly large, on the order of 10^24 or more. This staggering number fuels the search for extraterrestrial life and raises profound questions about our uniqueness and connection to the cosmos. Despite the vastness, the universe is governed by elegant laws of physics. Gravity shapes the motions of stars and galaxies, electromagnetism lights up stars and powers life, and nuclear forces fuse atoms to create the elements. These fundamental forces operate over enormous scales and times, linking the tiniest particles to the grandest cosmic structures. In contemplating the universe's size, we encounter a mixture of awe and wonder, science and philosophy. The numbers are so immense that they defy simple comprehension, but they tell a story about the origins, nature, and destiny of everything we know. The universe is a vast stage for the drama of existence, filled with infinite mysteries and endless beauty. By exploring its size, we embark on a journey that connects us to the stars, to the atoms within us, and to the fabric of space and time itself. As we explore the vastness of the universe, one of the most striking realizations is how much of it remains invisible to us. The observable universe, which extends about 46 billion light-years in every direction, contains everything we can detect through light and other forms of electromagnetic radiation. Yet, this observable portion is only a fraction of the entire universe, limited by the speed of light and the age of the cosmos. Beyond the veil of visible light, astronomers use different wavelengths, from radio waves to X-rays and gamma rays, to peer deeper into space and uncover hidden aspects of the universe. These wavelengths reveal phenomena invisible to our eyes, such as black holes, neutron stars, and the cosmic microwave background radiation. Black holes, for example, are regions of space-time where gravity is so intense that nothing, not even light, can escape. Though invisible themselves, black holes influence their surroundings, pulling in matter and emitting powerful radiation as gas and dust spiral inward. They serve as cosmic laboratories to test gravity and extreme physics. Neutron stars, the dense remnants of supernova explosions, are another extraordinary feature of the universe's complexity. Despite being only about 20 kilometers in diameter, they pack more mass than the sun and can spin hundreds of times per second, emitting beams of radiation detectable as pulsars. These extreme objects are scattered across the cosmos, often residing in distant galaxies billions of light-years away. Their study helps us understand the universe's energetic processes and the life cycles of stars, further adding to the immense scale and variety of cosmic phenomena. Moreover, the universe is filled with dark energy, a mysterious force that drives its accelerated expansion. Unlike matter, dark energy does not cluster or interact with light. Instead, it acts as a repulsive force on cosmic scales, pushing galaxies apart. Its presence challenges our understanding of physics and the ultimate fate of the cosmos. Scientists use large-scale surveys and satellites like the Planck Observatory to map the cosmic microwave background and track how the universe has expanded over time. These observations reveal that the universe is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The dominance of dark components shows that most of the universe is made of stuff we cannot see or directly detect. This invisible majority shapes the universe's structure and evolution, making our attempts to measure its size both fascinating and challenging. In addition to these cosmic ingredients, the universe is also home to enormous structures that dwarf galaxies. Galaxy clusters and superclusters span millions of light-years, weaving a cosmic web that defines the universe's large-scale architecture. One such example is the Laniakea supercluster, which includes the Milky Way among thousands of galaxies. Spanning over 500 million light-years, Laniakea is a massive gravitational basin, drawing galaxies into its vast embrace. This structure illustrates the universe's hierarchical nature, where smaller systems group into larger ones. Understanding these large-scale structures helps astronomers trace how matter clumped after the Big Bang, driven by gravity and the properties of dark matter. The patterns of galaxies form a cosmic fingerprint that encodes the universe's history and its fundamental laws. As we consider the universe's immense size, we also face the challenge of representing these vast scales in a way that is comprehensible. Scientists often use powers of 10 to express distances, showing how each step up represents a factor of 10 larger than the previous. For example, the Earth's diameter is about 10^7 meters. The distance to the Moon is around 10^8 meters, and the distance to the Sun is approximately 10^11 meters. Beyond that, distances expand exponentially. The nearest star is about 10^16 meters away, The Milky Way is roughly 10 or 21 meters across, and the observable universe extends to about 10 or 26 meters. These numbers help bridge the gap between human scale and cosmic scale, illustrating the vast gulf that separates us from the edges of the known universe. Despite its enormous size, the universe is also astonishingly interconnected. The forces of nature that govern the smallest particles also shape the largest galaxies. The carbon atoms in our bodies were forged in the hearts of dying stars billions of years ago, linking us intimately to the cosmos. In this grand cosmic narrative, the universe's size is not merely a measurement. It is a symbol of our quest for knowledge, our curiosity, and our place within the vastness. The numbers beyond imagination tell a story of creation, destruction, and endless wonder. As we continue to explore the universe, our understanding of its size, composition, and history will grow, inspiring new questions and new discoveries. The universe invites us to dream, to seek, and to marvel at the infinite. The concept of distance in the universe takes on a meaning far beyond what we experience on Earth. When astronomers speak of the distance to a galaxy millions or billions of light years away, they are describing how far light travels in a year, about 9.46 trillion kilometers. This unit of measurement, the light year, helps bridge the enormous scales of space with the finite speed of light. But even the light year can be misleading when we consider the universe's continuous expansion. The light we observe from distant galaxies began its journey billions of years ago, but since then, space itself has stretched, meaning those galaxies are now much farther away than the distance their light traveled. This leads to the notion of co-moving distance, a measurement that factors in the universe's expansion, giving the current distance to an object based on the expansion rate. For the most distant observable galaxies, this co-moving distance can be tens of billions of light years, even though their light took less time to reach us. To understand the universe's size, we must also appreciate that space itself is not static but dynamic. Einstein's theory of general relativity describes gravity as the curvature of space-time caused by mass and energy. This curvature shapes the universe's geometry and influences how distances are measured and perceived. Observations reveal that the universe is remarkably flat, meaning it follows the rules of Euclidean geometry on large scales. However, the universe's curvature is a subtle property, challenging to detect but crucial for understanding its overall size and fate. The cosmic horizon defines the limit of what we can observe, set by the age of the universe and the speed of light. Beyond this horizon lies space that we cannot see or influence, making our observable universe a cosmic bubble within a possibly infinite expanse. This boundary is not a physical edge, but a limit imposed by the time it takes light to reach us. As the universe ages and expands, this horizon grows, revealing new regions of space. Yet, due to accelerated expansion, some regions will forever remain beyond our reach. Inside this cosmic bubble, galaxies, stars, and planets form intricate structures. These structures range from the tiny scale of atoms to the grand scale of galaxy superclusters. Every scale tells a story of cosmic evolution, governed by the interplay of fundamental forces. One of the most spectacular phenomena related to size and scale is the concept of gravitational lensing. Massive objects like galaxy clusters can bend light from more distant objects, magnifying and distorting their images. This effect not only helps astronomers study distant galaxies, but also provides indirect evidence for dark matter. Through gravitational lensing, scientists can map the distribution of matter, visible and invisible, across vast cosmic distances. These observations deepen our understanding of the universe's structure and composition. Another profound measure of the universe's scale is the cosmic timeline. The universe is about 13.8 billion years old, a number derived from multiple lines of evidence including observations of the cosmic microwave background, the expansion rate, and the ages of the oldest stars. This age corresponds to the time since the Big Bang, the moment when the universe began expanding from a hot, dense state. Since then, the universe has grown and cooled, allowing matter to coalesce into galaxies and stars, and eventually planets, capable of supporting life. Time and space are intertwined in this cosmic evolution, reminding us that the universe is not just large in size but rich in history and dynamic in nature. Our place within this immense universe is both humble and extraordinary. The Earth orbits an ordinary star in a relatively quiet corner of the Milky Way galaxy. Yet from this vantage point, we have developed the technology and curiosity to measure the universe's size, composition, and fate. The universe's numbers may seem beyond imagination, but they represent real phenomena, real stars, galaxies, and cosmic events. They remind us that the cosmos is a vast, interconnected system, and that human beings are part of its ongoing story. As we gaze into the night sky, we are looking at light that has traveled across unimaginable distances and times. Each star's twinkle is a message from the past, a reminder of the universe's grandeur and mystery. Our understanding of the universe's size continues to grow with every new discovery. From the first telescopes to space-based observatories, like the Hubble and James Webb Space Telescopes, our ability to probe deeper into space and time improves constantly. These instruments reveal galaxies forming just a few 100 million years after the Big Bang, quasars blazing with energy from supermassive black holes, and the faint glow of the cosmic microwave background, a relic of the universe's earliest moments. With each new insight, the universe's immensity becomes clearer, yet the mysteries deepen. Questions about dark matter, dark energy, the multiverse, and the ultimate fate of the cosmos drive ongoing research and exploration. In the face of such vastness, human curiosity shines as brightly as any star. The desire to understand how big the universe is, why it exists, and what it contains reflects our profound connection to the cosmos. The universe's scale is a canvas on which the story of existence unfolds. It challenges us to dream big, think deeply, and explore the unknown. As we delve deeper into the scale of the universe, the concept of time itself becomes inseparable from distance. When we say a galaxy is a billion light-years away, we are saying that the light we see from it today left that galaxy a billion years ago. In a very real sense, telescopes are time machines, allowing us to peer back into epochs long before Earth, life, or even our sun existed. This journey through time and space reveals the universe's dynamic nature. Galaxies collide, stars are born and die, and cosmic structures evolve over billions of years. The scale of these events dwarfs human experience, yet they unfold according to physical laws that are consistent across the cosmos. The universe is also expanding at an accelerating pace, propelled by dark energy, an elusive force constituting roughly 68% of the universe's total energy density. This expansion means that distant galaxies are moving away from us faster than the speed of light, not because they are traveling through space faster than light, but because space itself is stretching. This phenomenon means some galaxies will eventually move beyond our observable horizon, slipping out of view forever. In this ever-expanding cosmos, the size of the observable universe today, about 93 billion light-years across, only tells part of the story. Beyond this horizon, the universe likely continues indefinitely, possibly infinitely, challenging us to rethink our notions of size and boundaries. In addition to sheer scale, the universe displays astonishing diversity in its contents. From tiny particles like neutrinos, zipping through space with nearly no mass, to massive galaxy clusters containing trillions of stars, the cosmic inventory is vast and varied. Stars themselves come in a dazzling range of sizes and types, from small, cool red dwarfs that can burn for trillions of years, to massive blue giants that live fast and die young in spectacular supernovae. Stars are the engines of cosmic evolution. They produce the elements necessary for planets and life, forging atoms heavier than hydrogen and helium through nuclear fusion. Galaxies also vary dramatically, from elegant spirals like our Milky Way, with its swirling arms and bright core, to massive elliptical galaxies filled with older stars, to irregular galaxies that defy simple classification. Each galaxy is a cosmic city, home to billions or trillions of stars, along with clouds of gas and dust. At the grandest scale, galaxies cluster together under the influence of gravity, forming vast superclusters and filaments separated by enormous voids. This cosmic web spans hundreds of millions of light-years and forms the large-scale structure of the universe. These structures are not static. Gravity pulls matter together, shaping galaxies and clusters, while dark energy pushes them apart. On the largest scales, this interplay determines the universe's ultimate fate, whether it will expand forever, slow down, or collapse back on itself. The mysteries of the universe's size and expansion are central to modern cosmology. They force us to confront profound questions about the nature of space, time, and reality. What is dark energy? What is the shape of the universe beyond our observable horizon? Are there other universes beyond our own? The quest to answer these questions drives technological innovation and international collaboration. From ground-based observatories to space telescopes, particle accelerators, to gravitational wave detectors. Our understanding of the universe's size has grown exponentially over the last century. Early astronomers believed the Milky Way was the entire universe. Then Edwin Hubble's discovery in the 1920s of galaxies beyond our own expanded the cosmic scale dramatically. Today, observations probe billions of light-years into the past and space, revealing a universe more vast and complex than ever imagined. Yet, with all we have learned, the universe remains a place of mystery and wonder. Its size is not just a number, but a symbol of humanity's endless curiosity and capacity for discovery. As we gaze up at the night sky, we are reminded that the universe is vast beyond comprehension, filled with light, darkness, matter, and energy, all woven into a cosmic tapestry that continues to expand and evolve. Our journey to understand how big the universe is has only just begun. It is a story of exploration, discovery, and the relentless human spirit seeking to comprehend the infinite. To grasp the vastness of the universe, one must also understand the concept of scale, not just physical distance, but the relationship between different scales of size and time. From the tiniest subatomic particles to colossal galaxy clusters, the universe spans an astonishing range of scales that challenge the limits of human comprehension. At the smallest end of the scale lies the quantum realm, where particles like quarks and electrons exist. These fundamental particles are the building blocks of matter, yet they behave in ways that defy classical intuition. Governed by probabilities and uncertainty, the laws of quantum mechanics describe this strange world, which underpins all of reality. Moving upward in scale, atoms combine to form molecules, the chemical basis of everything from air to living cells. These microscopic structures build the materials that make up planets, stars, and living organisms. Life itself emerges from complex molecular interactions occurring on incredibly small scales. Beyond molecules are planets and stars, celestial bodies that we can observe directly or infer from their effects. The Earth, about 12,700 kilometers in diameter, is a tiny speck compared to the Sun, which stretches nearly 1.4 million kilometers across. The Sun, a medium-sized star, is itself dwarfed by giants like Betelgeuse, which would engulf the orbit of Mars if placed at the center of our solar system. Stepping further out, stars group together into galaxies. Our home, the Milky Way, contains around 100 billion stars and spans about 100,000 light-years across. Yet, the Milky Way is just one of countless galaxies in the universe, each with its own unique structure and history. Galaxies themselves cluster in groups, which in turn form larger clusters and superclusters. These massive structures stretch across hundreds of millions of light-years, linked by filaments of dark matter and gas. These filaments create a cosmic web that shapes the universe's large-scale structure, with enormous voids in between where few galaxies exist. The universe's scale also includes time, a dimension often intertwined with space. The age of the universe, about 13.8 billion years, is linked to its size through the speed of light and cosmic expansion. The further we look into space, the further back in time we see, observing the universe's history unfolding. This cosmic timeline is not just a scientific concept, but a narrative of creation. From the hot, dense state of the Big Bang, through the formation of the first atoms, stars, galaxies, and ultimately planets capable of supporting life, the universe tells a story written across billions of years and unimaginable distances. The numbers involved in describing the universe's size can be daunting. Distances are measured in light years, parsecs, and megaparsecs. A parsec is about 3.26 light years, used by astronomers to measure distances within and between galaxies. Megaparsecs, millions of parsecs, describe scales of galaxy clusters and beyond. While the observable universe spans roughly 93 billion light-years in diameter, this is only the portion from which light has had time to reach us since the Big Bang. The total universe could be infinitely larger, or even infinite, a concept that challenges both science and philosophy. Understanding the universe's size requires sophisticated instruments. Space telescopes like Hubble and the James Webb, along with ground-based observatories, provide detailed images and spectra of distant objects. These data allow scientists to measure distances, compositions, motions, and ages. One of the most significant achievements of modern astronomy is the measurement of the Hubble constant, the rate at which the universe is expanding. This constant helps determine the universe's age and size and guides models predicting its future. However, recent measurements have revealed discrepancies in the Hubble constant's value, leading to intense debate and investigation. These tensions suggest that our understanding of cosmic expansion and the universe's size may need refinement, highlighting the ongoing nature of discovery. Beyond measuring size, astronomers seek to understand the universe's shape and topology. Is the universe infinite and flat, or does it curve back on itself like the surface of a sphere? Could it have a more complex topology, with a finite volume but no edges? Current evidence supports a flat, infinite universe on large scales, but subtle clues might one day reveal surprises. These possibilities inspire new theoretical and observational efforts to probe the cosmos's geometry. In considering the universe's size, one cannot ignore the role of dark matter, an invisible substance that exerts gravitational influence on galaxies and clusters. Dark matter forms the scaffolding upon which visible matter assembles, shaping the universe's structure across vast scales. Similarly, dark energy, the mysterious force accelerating cosmic expansion, dominates the universe's energy budget. Understanding these dark components is crucial to grasping the universe's size, fate, and ultimate nature. The vast numbers describing the universe can feel abstract and impersonal, but they also connect deeply to our existence. Every atom in our bodies was forged in stars billions of years ago, and the cosmic processes shaping the universe continue to influence our world. The universe's size and scale invite us to reflect on our place in the cosmos. We are small, yet capable of understanding and exploring vast distances. We are fleeting, yet part of an eternal cosmic dance. This awareness enriches our appreciation for the universe's beauty and complexity. It fuels the human spirit to learn, to dream, and to seek meaning in the infinite. In the end, the universe's size is more than a measure of distance. It is a testament to the boundless potential of nature and humanity's quest to comprehend the mysteries beyond imagination. The vastness of the universe compels us to confront one of the most profound questions. Are we alone? Within this almost incomprehensible expanse of space and time, the possibility of other life forms sparks both scientific inquiry and deep philosophical reflection. The sheer scale of the universe increases the likelihood that life exists elsewhere. With billions of galaxies, each containing billions of stars, many of which are orbited by planets in their habitable zones, the numbers quickly become staggering. The Drake equation, proposed to estimate the number of intelligent civilizations in our galaxy, encapsulates this vast potential. Yet despite the statistical probabilities, the search for extraterrestrial life remains elusive. Radio telescopes scan the skies for signals, space probes explore nearby planets and moons, and telescopes analyze exoplanet atmospheres for signs of habitability. Every discovery pushes the boundaries of what we know and reminds us of how much remains mysterious. Our understanding of the universe's size also shapes the scale of these searches. Signals traveling at the speed of light take years, decades, or millennia to reach us. If intelligent civilizations exist far away, communication across such vast distances poses enormous challenges. Meanwhile, the discovery of exoplanets, planets orbiting stars beyond our solar system, has transformed our view of the cosmos. Thousands of these worlds have been found, varying in size, composition, and distance. Some lie within their star's habitable zone, where liquid water might exist, a key ingredient for life as we know it. These findings ignite our imagination, suggesting that the universe's vast size may also harbor countless niches for life to flourish. The possibility of diverse life forms, from microbial organisms to advanced civilizations, expands the horizon of cosmic exploration. The universe's immensity also influences how we perceive time and change. On human scales, lifetimes and generations mark our experience. Yet, cosmic timescales span billions of years, during which stars are born, galaxies collide, and the universe itself evolves. This perspective fosters humility and wonder. It invites us to see ourselves as part of an ongoing cosmic story, connected to the past and future through the fabric of space and time. Moreover, the universe's size challenges our technological capabilities. Traveling to even the nearest star systems with current technology would take thousands of years. Thus, our exploration of the cosmos is primarily through observation, interpretation, and imagination. Advances in propulsion, artificial intelligence, and space exploration may one day extend humanity's reach further. Yet, even as we dream of interstellar travel, the numbers remind us of the immense distances and energy required. In contemplating the universe's size, we also confront the nature of infinity. Is the universe infinite in extent, or does it have boundaries beyond our observational horizon? The answer remains unknown, pushing the frontiers of both physics and philosophy. Some cosmological models propose a multiverse, a vast ensemble of universes beyond our own, each with different physical laws and properties. This concept, while speculative, expands the notion of size beyond our observable cosmos. The vast numbers that describe the universe provoke not only scientific inquiry, but also artistic and cultural expression. Poets, writers, and artists draw inspiration from the cosmos, weaving its grandeur into stories that capture human emotion and imagination. Through this interplay of science and art, the universe's size becomes a source of meaning and beauty, a reminder of the wonder that drives humanity forward. Ultimately, the universe's vastness is a call to explore, to reach beyond our limits, to question, and to seek understanding. It invites us to connect across space and time, to celebrate the mysteries that make existence profound. As we continue to measure, observe, and imagine, we honor the infinite scales that define our universe and our place within it. The universe's immense scale is often difficult to visualize. To bridge this gap, scientists use analogies and models that bring these vast numbers into relatable perspectives. Imagine for a moment shrinking the entire history of the universe into a single calendar year. In this cosmic calendar, the Big Bang occurs on January 1st at midnight, and today is December 31st, just seconds before midnight. On this timescale, the Milky Way galaxy forms around May. The solar system appears in early September, and Earth's first simple life forms emerge in late September. Human history, by comparison, occupies only the last few seconds of December. This analogy reveals how recent and fleeting our existence is on the cosmic stage. Similarly, when it comes to size, imagine shrinking the Earth down to the size of a marble. At this scale, the Sun would be a sphere about 2 meters in diameter, located about 200 meters away. The nearest star, Proxima Centauri, would then be over 40 kilometers distant. This model shows how empty and vast the spaces between stars truly are. Understanding the universe's scale also challenges our perception of motion and speed. While we often think of speed in everyday terms, the universe operates on velocities measured in thousands of kilometers per second. Light itself travels at nearly 300,000 kilometers per second, yet crossing the universe at this speed still takes billions of years. The expansion of the universe adds another layer to this complexity. Space itself stretches, carrying galaxies apart like dots on a balloon's surface as it inflates. This expansion means that distances between distant galaxies increase faster than light can travel, a phenomenon that redefines our understanding of speed limits in the cosmos. As we explore the universe's size, we must also consider the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation fills all of space and provides a snapshot of the universe when it was just 380,000 years old, a mere infant in cosmic terms. Studying this ancient light allows scientists to map the universe's large-scale structure and measure fundamental properties like its age, composition, and geometry. It acts as a cosmic blueprint, revealing clues about how the universe expanded from its initial conditions. The cosmic microwave background also connects to the concept of the universe's size because it marks the limit of the observable universe's earliest light. Beyond this boundary, the universe is opaque to electromagnetic radiation, hiding whatever may lie further back in time. New technologies, such as gravitational wave detectors, open additional windows into the universe's size and history. Gravitational waves are ripples in spacetime caused by massive accelerating objects, like merging black holes or neutron stars. Detecting these waves allows us to observe phenomena invisible to traditional telescopes. These observations complement our understanding of cosmic distances and timescales, providing a richer, multidimensional view of the universe. They demonstrate that the cosmos communicates with us through many channels, not just light. The interplay between the universe's immense size and the fundamental laws of physics reveals deep connections between the very large and the very small. Quantum mechanics governs the subatomic world, while general relativity describes the cosmic scale fabric of spacetime. The unification of these realms remains one of physics' greatest challenges. Understanding how big the universe is, therefore, involves grappling with mysteries that span both the tangible and the abstract. It calls for creativity, curiosity, and perseverance, a reflection of the human spirit. The enormity of the universe also inspires a profound sense of wonder and awe. It invites us to appreciate the delicate balance that allows galaxies to form, stars to shine, and life to emerge. In the vast cosmic ocean, our planet is a rare and precious oasis. Recognizing the universe's size encourages a global perspective, reminding us that Earth is a shared home and that our fate is tied to the cosmos. It urges stewardship, compassion, and unity in the face of challenges that transcend borders. In this light, the universe's scale is not just a scientific fact, but a source of inspiration. It teaches humility and resilience, curiosity and courage, challenges us to keep exploring, to keep asking, and to keep dreaming. The universe's numbers are staggering. Billions of galaxies, trillions of stars, unimaginable distances and times. Yet, within these vast numbers lies the story of everything, including us. As we stand on the brink of new discoveries, the universe's size invites us to look up with wonder and to reach out with hope. It is a vast, mysterious, and beautiful place, waiting for us to uncover its secrets. The vast expanse of the universe is a canvas painted with mysteries and marvels, each inviting us to explore deeper and question further. As we look beyond our immediate cosmic neighborhood, we encounter phenomena that stretch the limits of our understanding and challenge our imagination. One such phenomenon is the existence of black holes, regions in space where gravity is so intense that nothing, not even light, can escape. Black holes form from the remnants of massive stars collapsing, under their own gravity, or from the merging of dense stellar remnants. These cosmic enigmas embody extremes of physics and serve as natural laboratories for testing the laws of nature. Supermassive black holes, millions or billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. These titanic entities influence the formation and evolution of their host galaxies, shaping the cosmic landscape on scales spanning thousands of light years. The event horizon of a black hole marks the boundary beyond which information cannot escape, raising profound questions about the nature of information, space, and time. Hawking radiation, a theoretical prediction, suggests that black holes can slowly evaporate, linking quantum mechanics with gravity in ways that continue to fascinate scientists. Black holes illustrate the universe's extremes in size and density, highlighting the vast contrasts that exist within the cosmic fabric. From the near-invisible quantum particles to these cosmic giants, the universe encompasses an extraordinary range of scales. Beyond black holes, the universe is home to extraordinary cosmic events such as gamma-ray bursts, the most energetic explosions known. These brief but intense flashes of gamma rays can release more energy in seconds than the Sun will emit over its entire lifetime. Observing these bursts provides insights into stellar death, black hole formation, and the universe's early epochs. Similarly, neutron stars, the dense remnants of massive stars, pack the mass of our Sun into a sphere only about 20 kilometers across. Their magnetic fields and rapid rotation produce pulsars, cosmic lighthouses emitting beams of electromagnetic radiation, detectable across vast distances. These exotic objects not only deepen our understanding of matter under extreme conditions, but also serve as tools for measuring cosmic distances and testing gravitational theories. The universe's vast size also allows for cosmic coincidences and patterns that inspire awe. The large-scale structure, the cosmic web of galaxies and voids, resembles a vast, interconnected network, a pattern emerging from the interplay of gravity and dark matter. This cosmic architecture forms the backdrop against which galaxies grow, collide, and evolve. Studying these structures reveals the universe's history, its composition, and the processes that shaped it. As we explore these scales, we are reminded of the delicate balance between forces, gravity, electromagnetic interactions, nuclear forces, that govern cosmic evolution. This balance enables the existence of stars, planets, and ultimately, life. The vastness of the universe also inspires humility. In the face of such immense scales, human concerns seem small, yet this perspective can empower us to appreciate the preciousness of life and the unique opportunity we have to explore and understand. Our technological progress reflects this aspiration. Instruments like the Very Large Telescope, the Atacama Large Millimeter, Submillimeter Array, and the upcoming Extremely Large Telescope push the boundaries of resolution and sensitivity, bringing the distant universe into clearer focus. Space missions such as the Voyager probes have journeyed beyond the solar system, venturing into interstellar space, carrying messages from humanity. These endeavors symbolize our drive to transcend our earthly origins and connect with the cosmos. In contemplating the universe's vastness, we are also drawn to philosophical reflections. The universe's size challenges our notions of meaning, purpose, and existence. Are we a cosmic accident or part of a grand design? Does the universe have a beginning and an end, or is it eternal? These questions have engaged thinkers across cultures and epochs, intertwining science with philosophy, spirituality, and art. The numbers that describe the universe's size, billions of light years, trillions of stars, are more than abstract figures. They are a testament to the complexity and richness of existence. Every atom in our bodies was forged in stars billions of years ago. We are, in a very literal sense, children of the cosmos. This connection gives a profound meaning to the universe's vastness, linking us intimately to the stars. As we continue to unravel the universe's mysteries, we do so not just as observers, but as participants in its ongoing story. The universe's size invites us to embrace curiosity, wonder, and a sense of shared destiny. It is a call to explore, to learn, and to imagine. A reminder that in the vastness of space and time, our quest for understanding is itself a luminous beacon. The enormity of the universe invites us to think not only about spatial dimensions, but also about the richness of phenomena occurring across its vast expanse. From the simplest atoms to the most complex galaxies, the universe is a dynamic stage where matter and energy interact in endlessly fascinating ways. One of the most remarkable features of the universe is the process of star formation. Within giant molecular clouds, vast cold regions filled with gas and dust, gravity slowly pulls matter together. Over millions of years, dense cores collapse, heating up until nuclear fusion ignites, birthing new stars. These stellar nurseries, often visible as glowing nebulae, represent the cycles of creation and destruction that sustain the cosmos. Stars live and die, enriching their surroundings with heavier elements forged in their cores, or during explosive deaths called supernovae. These heavy elements, from carbon to iron and beyond, form the building blocks of planets, organic molecules, and ultimately life. In this way, the universe's vastness is intimately tied to the emergence of complexity. Galaxies, the grand assemblies of stars, gas, and dark matter, exhibit diverse forms and histories. Some are spiral-shaped like the Milky Way, with graceful arms swirling around a central bulge. Others are elliptical or irregular, shaped by gravitational interactions and cosmic collisions. These galactic encounters, occurring over millions of years, trigger bursts of star formation and dramatically alter galactic structure. Such interactions remind us that the universe is not static, but constantly evolving. Clusters of galaxies, bound by gravity, represent the largest gravitationally bound structures known. They contain thousands of galaxies, along with vast amounts of hot, X-ray emitting gas. Studying these clusters helps scientists understand the distribution of dark matter in the universe's large-scale structure. The universe's immense size also allows for the existence of cosmic phenomena that challenge human comprehension, such as cosmic inflation, a brief period of rapid expansion just after the Big Bang. Inflationary theory explains the observed uniformity and flatness of the universe and the origin of tiny density fluctuations that seeded galaxy formation. The concept of inflation extends our understanding of the universe beyond what we can observe directly, suggesting that our observable universe is just a small part of a much larger, possibly infinite cosmos. At the largest scales, the universe exhibits homogeneity and isotropy, meaning it looks roughly the same in all directions and locations. This cosmological principle forms the foundation of modern cosmology and supports the use of simplified models to describe cosmic evolution. Yet subtle variations in the cosmic microwave background radiation reveal the seeds of structure formation, highlighting the interplay between simplicity and complexity in the cosmos. The numbers involved in these processes are mind-boggling. Consider that a typical galaxy contains billions of stars, each potentially hosting multiple planets. Multiply this by the estimated 2 trillion galaxies in the observable universe, and the scale of possible worlds becomes nearly unimaginable. This abundance fuels scientific efforts to find habitable planets and extraterrestrial life. Missions like Kepler and TESS have identified thousands of exoplanet candidates, some within habitable zones where conditions might support liquid water. The search for life beyond Earth continues to be one of humanity's most profound quests, driven by the recognition that the universe's size and diversity offer countless opportunities for life to arise. The universe's scale also influences the concept of cosmic horizons, limits beyond which we cannot see or interact. The observable universe is bounded by the distance light has traveled since the Big Bang. Beyond this horizon lies a vast, unobservable region, potentially containing endless more galaxies and phenomena. This limitation reminds us that our knowledge, though vast, is still partial. The universe holds secrets forever beyond our reach, inviting humility and ongoing curiosity. Technological advances continually push the boundaries of observation. Next-generation telescopes, space missions, and detectors promise to reveal ever fainter objects, deeper cosmic times, and new phenomena. Each discovery enriches our understanding and reshapes our sense of scale, revealing layers of complexity previously unseen. In contemplating these vast scales and profound phenomena, we find a reflection of our own journey toward knowledge, meaning, and connection. The universe's size is not just a measure of distance, but a gateway to understanding existence itself. It calls us to explore, to question, and to dream beyond limits. In the dance of galaxies and stars, in the quiet glow of distant nebulae, and in the faint echoes of the Big Bang, we see the universe's grandeur and our place within it. The vastness of the universe extends not only across space, but also through the fabric of time. Time itself is woven into the cosmic tapestry, stretching billions of years from the Big Bang to the present moment, shaping the evolution of everything. Within, when we observe distant galaxies, we are actually looking back in time. Because light takes time to travel, the photons reaching our telescopes from a galaxy a billion light-years away left their source a billion years ago. Thus, telescopes become time machines, revealing the universe's history layer by layer. This ability to peer back through time transforms our understanding of cosmic evolution. We witness galaxies forming, merging, and aging. We see the gradual enrichment of the cosmos with heavier elements as generations of stars live and die. Moreover, the expansion of the universe affects how we interpret these distant signals. Due to cosmic expansion, light from distant galaxies is stretched to longer wavelengths, a phenomenon known as redshift. Measuring redshift allows astronomers to determine how far away objects are and how fast the universe is expanding. The discovery of the accelerating expansion of the universe, attributed to a mysterious force called dark energy, revolutionized cosmology. Dark energy constitutes about 70% of the total energy content of the cosmos, pushing galaxies apart at an ever-increasing rate. This accelerating expansion suggests a future in which galaxies beyond our local group will move beyond our observable horizon, making the universe seem emptier over time. Such a future is both awe-inspiring and humbling. The interplay of dark energy, dark matter, and ordinary matter dictates the universe's large-scale structure and fate. Dark matter, invisible yet detectable through gravitational effects, acts as a cosmic scaffold around which galaxies form. Together, these unseen components reveal that the universe's visible matter, the stars, planets, and gas we can see, is only a small fraction of its total makeup. This realization reshapes our understanding of what the universe is and how it behaves. The universe's size and age also frame the search for extraterrestrial intelligence. If civilizations exist elsewhere, the vast distances and time delays pose significant communication challenges. A signal sent today to a star 1,000 light-years away would take a millennium to arrive. This cosmic isolation prompts us to consider the rarity and fragility of intelligent life. It also encourages efforts like the SETI, Search for Extraterrestrial Intelligence Program, which scans the skies for artificial signals that might indicate other minds. The enormity of the universe inspires deep philosophical reflections. It prompts us to ask what it means to be human in a cosmos that is billions of years old and billions of light-years across. Some find comfort and meaning in the idea that we are part of a vast, interconnected whole. Others grapple with the solitude that such vast distances imply. These questions have no easy answers, but drive humanity's ongoing quest for knowledge. As we look outward, we also look inward, examining our own place in the universe, the origins of life, and the nature of consciousness. The universe's scale magnifies the significance of these questions, making each discovery a step toward understanding the profound mystery of existence. Our technological advances continue to extend our reach into space and time. Future observatories, such as the James Webb Space Telescope and next-generation ground-based telescopes, will push the boundaries of observation further back toward the cosmic dawn. These instruments promise to reveal the first stars and galaxies, shedding light on the universe's earliest epochs and the processes that shaped everything we see today. In this grand cosmic journey, every measurement, every image, and every insight deepens our appreciation of the universe's grandeur and complexity. The universe's size, measured in billions of light-years and ages spanning billions of years, is a testament to the incredible scales of nature. It challenges our minds, expands our horizons, and stirs our spirits. As we contemplate these numbers, beyond imagination, we are reminded that the quest to understand the universe is also a journey to understand ourselves. The universe is an extraordinary canvas of light, stretching across unimaginable distances and spanning epochs beyond human comprehension. Light serves as our primary messenger, carrying information across the vast cosmic void, allowing us to piece together the story of existence. Yet, light has its limits. Traveling at approximately 299,992 kilometers per second, it is the fastest entity in the cosmos. But even light takes millions or billions of years to reach us from distant galaxies. This finite speed creates a cosmic horizon, a boundary beyond which we cannot see, because the light has not had time to arrive since the beginning of the universe. This horizon defines the observable universe, a sphere roughly 93 billion light-years in diameter, containing everything we can detect with our instruments. Beyond it lies the unobservable regions of space forever hidden from our view, potentially infinite in extent. The cosmic horizon reminds us that our understanding is inherently limited by the vast scales involved. It instills a sense of humility, acknowledging that even as our technology advances, some parts of the universe will remain forever beyond our grasp. Astronomers use redshift, the stretching of light waves due to cosmic expansion, to measure distances and look further back in time. The higher the redshift, the farther and older the object. Observations of galaxies with redshifts greater than 10 reveal the universe when it was less than 500 million years old. These distant observations are snapshots of the universe's infancy, a time when the first stars and galaxies ignited, ending the cosmic dark ages. This era marks a pivotal chapter in the universe's history, setting the stage for the complex structures we see today. The universe's size also brings into focus the concept of cosmic microwave background radiation, CMB, the relic radiation from the Big Bang. The CMB bathes the universe uniformly, offering a snapshot of the cosmos at just 380,000 years old, when photons decoupled from matter and began traveling freely through space. Studying the CMB's minute temperature fluctuations reveals information about the universe's geometry, composition, and evolution, confirms that the universe is flat on large scales, and that dark energy dominates its current expansion. The sheer scale of the universe means that it contains phenomena beyond everyday experience. For instance, gravitational lensing, where massive objects bend and magnify the light from more distant sources, allows astronomers to see galaxies otherwise hidden. This cosmic magnifying glass provides a window into the distant universe, enabling studies of galaxy formation and the distribution of dark matter. The universe's vastness also allows for the formation of large-scale structures, clusters, superclusters, filaments, and voids, collectively known as the cosmic web. This network forms the backbone of the universe, tracing the distribution of matter shaped by gravity over billions of years. These structures span hundreds of millions of light-years, dwarfing even entire galaxies in scale. Their existence testifies to the dynamic and interconnected nature of the cosmos. In the face of such enormity, it is natural to ask, how do we measure distances on this colossal scale? Astronomers use a cosmic distance ladder, a series of interlinked methods starting from nearby objects and extending outward. From parallax measurements for nearby stars to standard candles like Cepheid variables and type Ia supernovae, each rung builds upon the previous, allowing us to measure distances billions of light-years away. These techniques underpin our understanding of the universe's size, age, and expansion, anchoring abstract numbers in observable phenomena. Yet, the universe's scale also challenges our sense of time. Events spanning millions or billions of years contrast sharply with human lifespans. This contrast invites reflection on the fleeting nature of existence and the enduring legacy of cosmic processes. Despite the overwhelming numbers, the universe's vastness is not devoid of meaning. Rather, it is a source of inspiration and wonder, a testament to nature's grandeur and the endless possibilities it holds. Every star, every galaxy, and every particle contributes to the cosmic story, connecting us to something far greater than ourselves. The universe's size is a reminder of both our smallness and our significance, a paradox that drives scientific exploration and philosophical contemplation alike. As we continue to gaze into the depths of space and time, we carry with us the curiosity and determination to understand the cosmos, to find our place within it, and to embrace the mysteries that lie beyond. When we speak of the universe's size, we inevitably confront the astonishing concept of scale, scales so vast that they defy our everyday intuition. The universe stretches across billions of light-years, yet within it lie structures and phenomena that range from the unimaginably small, like quarks and photons, to the unfathomably large, like superclusters of galaxies. To grasp the enormity of the cosmos, it helps to consider the hierarchy of cosmic structures. At the smallest, subatomic particles dance in quantum realms, governed by probabilities and strange behaviors that challenge classical logic. Moving upward, atoms combine to form molecules, planets, stars, and then galaxies. Galaxies group together in clusters containing hundreds or thousands of members. These clusters assemble into superclusters, vast conglomerates spanning hundreds of millions of light-years, linked by filaments of dark matter and gas. Between these colossal structures lie immense voids, cosmic deserts almost devoid of galaxies, stretching tens of millions of light-years across. The contrast between dense clusters and empty voids paints a universe of remarkable complexity. This cosmic web, formed over billions of years by gravity pulling matter into filaments and nodes, is the large-scale skeleton of the universe. It reveals how matter is distributed on the grandest scales and how the universe has evolved since its earliest moments. Understanding these scales requires scientific ingenuity. Astronomers use light across the electromagnetic spectrum, from radio waves to gamma rays, to peer into different cosmic environments. Each wavelength unveils different aspects of celestial objects and phenomena. For example, radio telescopes detect cold gas clouds and cosmic microwave background radiation, while X-ray telescopes reveal the hot gas in galaxy clusters and the violent surroundings of black holes. The universe's scale also influences the passage of time in fascinating ways. According to Einstein's theory of relativity, time is not absolute but relative, affected by gravity and velocity. Near massive objects like black holes, time slows relative to distant observers, a phenomenon known as time dilation. This means that the flow of time itself varies across the universe's vast landscape. The interplay between space, time, and gravity forms the foundation of modern physics and shapes our understanding of reality. Consider also the expansion of space itself. Since the Big Bang, the universe has been stretching, causing galaxies to move away from each other. The farther a galaxy is, the faster it appears to recede, a relationship described by Hubble's law. This expansion creates an ever-growing cosmic horizon, beyond which galaxies move away faster than light due to space itself expanding. These galaxies become forever unreachable, lost beyond our observational grasp. The discovery of dark energy, the mysterious force driving the universe's accelerated expansion, adds another layer of wonder. Dark energy's nature remains one of the greatest puzzles in physics, with profound implications for the universe's fate. Will the universe expand forever, growing colder and emptier? Or will some unknown process alter its course? These questions drive current research and fuel our curiosity about the cosmos. Despite the vastness, the universe feels intimately connected to us. Every element heavier than hydrogen and helium was forged in the heart of stars. These stellar forges created the building blocks of planets, life, and consciousness. This cosmic heritage links us directly to the universe's grand scale. We are, quite literally, made of stardust, a profound truth that inspires awe and a sense of belonging. In our quest to measure and comprehend the universe, humanity has developed remarkable tools and techniques. From ground-based observatories, perched atop remote mountains, to space telescopes orbiting Earth, we continue to extend our cosmic reach. Future missions and instruments promise to delve deeper, capturing light from the universe's first moments and unveiling the nature of dark matter and dark energy. The journey to understand the universe's size is ongoing, a testament to human curiosity and perseverance. Each new discovery enriches our cosmic story and expands the horizon of our knowledge. In contemplating the universe's vastness, we embrace both mystery and discovery, awe and understanding. The universe's size is a gateway to exploring the nature of reality itself, inviting us to look beyond the familiar and into the infinite. The vast expanse of the universe is more than just a measure of distance. It is a journey through the very fabric of existence. As we consider the universe's scale, we are compelled to explore not only the spatial dimensions, but also the nature of the space itself. Space is not an empty void, but a dynamic entity, woven together with time to form the four-dimensional continuum known as space-time. Einstein's theory of general relativity revolutionized our understanding of gravity by describing it as the curvature of space-time caused by mass and energy. This curvature guides the motion of planets, stars, and galaxies, shaping the universe's architecture on every scale. Space-time itself can stretch and expand, a phenomenon first observed through the redshift of distant galaxies. This expansion reveals that the universe is not static but evolving, with galaxies receding from one another as the fabric of space grows. The universe's expansion is accelerating, a discovery that led to the concept of dark energy, a mysterious force permeating space, pushing it apart. Dark energy accounts for approximately 70% of the total energy content of the universe, yet its nature remains one of the deepest enigmas in physics. The implications of this accelerated expansion are profound. Over billions of years, distant galaxies will move beyond our observational horizon, becoming unreachable and invisible. The night sky will gradually darken, leaving only the closest galaxies and stars in view. This cosmic fate, sometimes called the Big Freeze, envisions a future where the universe grows colder and emptier, stars burn out, and matter becomes increasingly sparse. Despite this distant and chilling future, the present universe teems with complexity and wonder. From the formation of stars in swirling nebulae to the delicate balance of forces that allow planets to host life, the cosmos is a place of constant transformation. The interplay between matter and energy, governed by physical laws, creates structures that span from microscopic particles to enormous galaxy clusters. One of the most awe-inspiring phenomena in the universe is the existence of black holes, regions where gravity is so intense that not even light can escape. These cosmic enigmas distort space-time, challenge our understanding of physics, and serve as natural laboratories for extreme conditions. Supermassive black holes, millions to billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. Their immense gravity influences the dynamics and evolution of galaxies on large scales. Black holes also emit powerful jets of energy and radiation, shaping their environments and providing clues about the behavior of matter and energy under extreme gravity. On smaller scales, the quantum realm reveals the universe's intricate inner workings. Quantum mechanics governs the behavior of particles at the smallest scales, introducing principles like uncertainty and entanglement that defy classical intuition. This duality between the vast and the tiny, between cosmic grandeur and quantum mystery, highlights the universe's layered complexity. Scientists continue to seek a unified theory that reconciles general relativity and quantum mechanics, hoping to unlock a deeper understanding of the universe's origins and fundamental nature. The universe's size and complexity invite endless exploration, inspiring generations to look upward and outward with wonder and determination. Our ability to measure, observe, and theorize about such vast scales is a testament to human ingenuity and curiosity. Every photon captured, every signal decoded, every equation formulated brings us closer to grasping the universe's true scale and meaning. In contemplating the infinite, we are reminded that the universe's enormity is matched only by the potential of human imagination and discovery. The universe, in all its vastness, humbles us with the scale of its distances and the immensity of its mysteries. As we continue to explore the cosmos, one question emerges with greater urgency. Are we alone? The sheer size of the universe suggests that the conditions for life may have arisen many times across the cosmic expanse. Yet we have yet to find definitive evidence. The search for extraterrestrial life is one of humanity's most profound endeavors. It spans many fields, from astronomy and biology to chemistry and planetary science, each contributing to understanding how life might arise elsewhere. One key to this search is the identification of exoplanets, planets orbiting stars beyond our solar system. Since the early 1990s, thousands of exoplanets have been discovered, many residing in the so-called habitable zone, where temperatures could allow liquid water to exist. Water is essential to life as we know it, making these planets prime targets for further study. However, habitability depends on many factors: atmospheric composition, magnetic fields, geological activity, and more. Beyond individual planets, scientists study the chemistry of interstellar space, where complex organic molecules have been detected. These molecules could be precursors to life's building blocks, suggesting that the ingredients for life may be widespread. Astrobiology investigates how life might survive and evolve under different conditions, broadening our conception of what life could be beyond Earth. The vastness of the universe means that the nearest habitable exoplanets are still many light years, making direct exploration currently impossible. Instead, scientists rely on telescopic observations and spectroscopy to infer atmospheric compositions and potential biosignatures. The quest to detect signals from intelligent civilizations fuels programs like SETI, which listens for deliberate radio or laser transmissions. Although no confirmed signals have yet been found, the search continues with ever-increasing sensitivity. This cosmic silence prompts reflection on the Fermi paradox. If the universe is so vast and potentially life-friendly, why have we not yet detected signs of other civilizations? Possible answers range from the rarity of life to self-destruction of civilizations or the challenges of interstellar communication. Despite uncertainties, the search itself reflects humanity's desire to connect and understand our place in the cosmos. Our understanding of the universe's size frames this quest, highlighting both the opportunity and the challenge. The vast distances stretch the imagination and the limits of technology, requiring patience and persistence. Meanwhile, the study of our own solar system offers clues about life's resilience. Moons like Europa and Enceladus harbor subsurface, oceans beneath icy crusts, environments that might support microbial life. Mars, with its history of water and current conditions, remains a prime target for exploration. Missions like Perseverance are searching for signs of past life, expanding our understanding of habitability. The enormity of the universe invites us to think beyond Earth-centric perspectives, embracing a cosmic view of life and existence. This perspective inspires a sense of unity and shared destiny, whether life is unique to Earth or abundant across the stars. Ultimately, the universe's vast scale is a call to wonder, a reminder that exploration is both a scientific pursuit and a deeply human endeavor. As we peer into the cosmos, seeking answers to these timeless questions, we deepen our connection to the universe and to each other. The immensity of the universe challenges our understanding of existence in profound ways. It forces us to reconsider notions of time, space, and even reality itself. As we explore the universe's vast dimensions, we encounter phenomena that stretch our minds and inspire new ways of thinking. One such phenomenon is the multiverse hypothesis, the idea that our universe might be just one of countless others. According to some theories, there may be an infinite number of universes, each with its own laws of physics, constants, and histories. This concept, though speculative, arises from attempts to reconcile quantum mechanics, cosmic inflation, and string theory. It suggests that the cosmos we observe is only a small part of an unimaginably larger reality. If the multiverse exists, the size of reality itself expands beyond anything we can truly comprehend, pushing the boundaries of imagination and science alike. The multiverse theory also provides a framework to address the fine-tuning problem, in the observation that the physical constants of our universe appear precisely calibrated to allow the emergence of life. In a multiverse setting, countless universes exist with varying parameters, and we happen to reside in one where conditions are right for life. While intriguing, the multiverse remains a challenging idea to test empirically. The limits of observation constrain us to our own universe, and the existence of others may forever remain a philosophical question. Nonetheless, such ideas inspire us to explore deeper, question assumptions, and expand the horizons of cosmology. In parallel, the study of cosmic inflation, an era of rapid exponential expansion shortly after the Big Bang, helps explain the universe's large-scale uniformity and flatness. Inflation theory posits that within a tiny fraction of a second, the universe ballooned from subatomic scales to macroscopic dimensions, setting the stage for the vast cosmos we see today. This rapid growth smooths out irregularities, creating the near-uniform cosmic microwave background and the large-scale structures that follow. Inflation also offers a mechanism for the creation of the universe itself, a moment when space and time emerged from a quantum fluctuation, beginning the Pleistocene grand cosmic story. The numbers associated with inflation are staggering. In less than 1/trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor of at least 10 to 26, making it unimaginably larger in almost no time at all. These mind-boggling numbers challenge human intuition but are essential to explaining how a universe so vast and complex could arise from seemingly nothing. Moreover, the concept of time itself becomes nuanced at these extremes. Quantum gravity and theories of everything seek to unify general relativity, with quantum mechanics to describe the universe's earliest moments. Understanding this initial singularity, the birth of space, time, and matter, is one of modern physics' greatest quests. The universe's vastness, therefore, is not just a measure of distance, but a story of origins, evolution, and the fundamental nature of reality. Each discovery peels back a layer of mystery, revealing new questions and deeper insights. This ongoing journey transforms the numbers beyond imagination into a narrative of cosmic wonder and human curiosity. It reminds us that the universe's grandeur is matched only by the depth of our desire to understand it. The universe is a profound testament to the power of scale not only of size, but of time, energy, and complexity. As we traverse its vastness, we encounter epochs that stretch across billions of years, events that release energies beyond comprehension, and structures of staggering intricacy. The age of the universe, estimated at approximately 13.8 billion years, anchors our understanding of cosmic history. This time span encompasses the birth of the first atoms, the ignition of the earliest stars, and the assembly of galaxies into the cosmic web. It is a narrative woven with threads of light and matter, guided by the fundamental forces of nature. Throughout this vast timeline, Energy has played a pivotal role. The universe's earliest moments were dominated by unimaginably intense energies, setting conditions that shaped everything to come. From the searing heat of the Big Bang to the gentle warmth of stars, energy has sculpted the cosmos and powered the processes that allow complexity to emerge. Consider the Sun, a relatively modest star in our galaxy. It fuses hydrogen into helium, releasing immense energy that sustains life on Earth. This fusion process converts mass into energy, illustrating Einstein's famous equation, E=mc2, which reveals the deep connection between mass and energy. On a grander scale, galaxy collisions release gravitational energy that can trigger star formation and reshape cosmic structures. These energetic processes span many orders of magnitude, from the subatomic to the intergalactic, demonstrating the universe's layered complexity. The interplay of forces, gravity, electromagnetism, and the strong and weak nuclear forces governs these phenomena, orchestrating the cosmic dance. In addition, the universe's vastness allows for diversity on a scale that defies imagination. Stars come in various sizes and lifespans, from tiny red dwarfs burning steadily for trillions of years, to massive blue giants that explode spectacularly as supernovae within millions of years. Planets vary widely in composition and environment, some scorching and barren, others cold and potentially habitable. This diversity extends to galaxies as well, from elegant spirals like the Milky Way to massive elliptical galaxies and irregular shapes, each telling a unique story of formation and evolution. The universe's sheer scale means that even rare and extreme phenomena become common when viewed in totality. Gamma-ray bursts, some of the most energetic events known, occur frequently somewhere in the cosmos, releasing more energy in seconds than our sun will produce in its entire lifetime. Similarly, neutron stars and black holes exist in staggering numbers, remnants of massive stellar deaths scattered throughout the universe. As we explore these extremes, our understanding of physics is tested and expanded. Observations of distant quasars, active galactic nuclei powered by supermassive black holes, push the boundaries of knowledge about matter and energy under extreme conditions. Moreover, the universe's vastness challenges us to think about its ultimate fate. Will it continue to expand forever, grow cold and dark? Will it experience a big crunch, collapsing back into a singularity? Or will new physics alter its destiny? These questions remain at the frontier of cosmology, with answers hidden in the fabric of space, time, and energy. The universe's size is thus a gateway to understanding fundamental questions about existence, origin, and destiny. It invites us to contemplate not only the immensity of space but also the depth of time and the scale of forces shaping reality. Through this lens, the universe becomes a vast laboratory, a grand narrative, and an enduring source of wonder. As we reach the horizon of our journey through the universe's vastness, we are reminded that size alone cannot capture the full grandeur of the cosmos. The universe is not just immense in scale, it is profound in meaning, complexity, and mystery. Its enormity challenges our imagination, pushing the boundaries of human thought and inspiring generations to look beyond themselves. Within the countless stars, galaxies, and cosmic structures lies the story of creation, a story that includes us, the atoms in our bodies, the forces that govern life and matter, the laws of physics, all connect us to this grand cosmic tapestry. The numbers that describe the universe's size, billions of light years, trillions of stars, uncountable particles, are more than mere statistics. They are the language of existence itself, telling a tale of time, space, and energy intertwined. Yet, even as science uncovers these vast quantities, it also reveals the delicate balances that make life possible. The universe's size and complexity create a setting for wonder, discovery, and profound questions about purpose and place. The cosmic horizon invites us to keep exploring, to seek knowledge beyond the limits of our current understanding. Every measurement, every observation, every theory builds upon centuries of human curiosity and ingenuity. As we gaze at the night sky, we stand at the edge of the infinite, connected to everything that ever was and ever will be. The universe's immensity is a mirror reflecting our own desire to know, to understand, and to find meaning in the vastness. In embracing these numbers beyond imagination, we embrace the awe and mystery that drive the human spirit. Our journey into the cosmos is ongoing, an unending quest that transforms the vastness from a distant concept into a personal voyage of discovery. The universe, in all its staggering magnitude, invites us to dream, to learn, and to marvel at the extraordinary. And in that invitation we find a profound truth, that even amidst the infinite, our place is unique, precious, and deeply connected to the cosmic story.